Good morning, everybody. Hope you're all healthy and safe. So, today we are going to begin our next module. Module 3. I'll be discussing with module 3. So, module 3, section 4.1, and it is about Laplace Transform. So, what is actually this Laplace Transform, or why do we need it? So the thing is, if you recall your integration and differentiation process, you're given a function, say f of x is equal to x square. So when we differentiate that function, it becomes 2x, and when we integrate it, it becomes x cube, right, by 3. So actually this differentiation and integration is actually transforming the given function into some other function. Okay, so Laplace transform is also another type of, or another method, or another way in which we can transform one function into another. Okay, so integration and differentiation, so far we have been doing integration and differentiation, that is also a kind of transform. Laplace transform is also another way of transforming the integration, the given function into another particular function. Now the benefit of using Laplace transform is that, like, apart from what should I say, we know that integration and differentiation are linear, right? D by dx of f plus g is equal to d by dx of f plus d by dx of g. Similar for integration. Apart from this linearity, there are many other properties of Laplace transform which can be used in practical level, and also that's why we are learning this transform, which is the Laplace transform. One another point that I want to discuss with you guys is, if you recall, when we find the integration, or when we calculate the integration of a function of two variables, suppose f of xy is a function given to us, if we integrate that function with respect to one variable, say suppose I am integrating f of xy with respect to x. Okay, so the integral can be definite, indefinite, whatever it is, and after the integration process we will get the function, we'll get another function, and that will be in terms of the other variable, right? Because we are not applying any values, or we are not giving any values to the variable y. So that is another property which we'll be using for Laplace transform, that is, we'll have a function in terms of s and t. Okay, here small letter s and small letter t. So usually we'll be given a function f of t, given a function in terms of t, and after applying the Laplace transform, it will become a function in terms of s. Okay, so let's just move on to what is Laplace transform. So this is the definition. Let f be a function defined for t greater than equal to 0. The integral 0 to infinity e raised to minus st f of t dt. This is called the Laplace transform, and it is denoted by script L of f of t. Okay. So what is a Laplace transform? It is, for any given function, we have to multiply it with e raised to minus st and integrate it from 0 to infinity. And there is one more condition, that is, since it is indefinite, like it is from 0 to infinity, the condition is that the integral must be convergent, then only we'll get a particular value. Okay, so most of the cases which we are dealing, or in this section and the following sections and all, they are all convergent. So this is the definition of L of f of t, script L of f of t, that is the Laplace transform of a given function in terms of t. So as I stated before, this is the integration is to be done with respect to t, and we have the variable s over here remaining, right? So the value that we get will be actually a function in terms of s. Okay, so the notation that we'll be using is script L of f of t, okay, is some function in terms of s. Okay, So in this throughout this textbook, what they are using is whatever function is given to us, f of t, g of t, h of t, L of f of t will be the corresponding uppercase letter. So L of I hope you understand, that is L of g of t will be some value, and that will be denoted by capital G of s. Okay, and L of h of t will be capital H of s, and so on. Okay, this is just used throughout the textbook in this manner. So this is the Laplace transform. So what we'll do in this section is we will find the Laplace transform of some particular functions, and make yourself familiar with the process of determining the Laplace transform. So we shall be discussing the mainly some simple Laplace transforms, transforms of simple functions in the very beginning, which we'll be using throughout later. So first of all, let us determine first one, 1. Okay, we shall determine what is L of 1. Now by definition, L of 1 is nothing but integral 0 to infinity e raised to minus st into f of t. F of t is here 1. Okay, here I'll just write it out. F of t is 1, that is a constant function. So into 1 into dt, that is nothing but integral 0 to infinity e raised to minus st dt. Now what is the integral of e raised to minus st? It will be e raised to minus st by minus s, right? And the limiting value is from 0 to infinity. Now we know e raised to minus infinity is 0, and e raised to 0 will be 1. So this will be actually minus of e raised to minus infinity into s by s. I'm just writing to make it clear. Minus e raised to minus s into 0 by s. Okay, so this is 0, minus into minus is plus, and we get the value to be, this is e raised to 0 is 1, so we get it as 1 by s. So script L, that is the Laplace transform of the constant function 1, is 1 by s. Okay, that's it. This is the only process. So we have to be familiar with the process of integration to determine the Laplace transform. Now let's do another simple example, that is to determine L of t. Okay, so by formula we know L of t is equal to integral 0 to infinity e raised to minus st into f of t. Here f of t is t, f of t into dt. So here we'll have to apply the integration by parts. So this will be nothing but this will be my first function, this will be my second function. So that will be t into integral of the second function, that is e raised to minus st by minus s, varying from 0 to infinity, minus 1, the derivative of the first function, that is d by dt of t, that is 1, into integral of again e raised to minus st into dt. Okay, so this we get it as t into e raised to minus st by s, varying from 0 to infinity. Now I'm sorry, this is so whole integral, right? This is our integration by parts, that is the integral of second function into the first function minus derivative, integral of derivative of the first function into integral of second function. So there is one more integral over here. Okay, now what is the integral of this value? This is minus minus, that is what we have done right now, e raised to minus st by s. Again there is one more integral sign. Okay, now this is nothing but, now let me apply the limits in this case. E raised to minus infinity is again 0, then we have t is 0, so 0, so this term is 0, and minus into minus is plus, and we get 0 to infinity e raised to minus st by s into dt, right? So I'm going to take 1 by s common from this, integral 0 to infinity e raised to minus st dt. I can write this as 1 by s into integral 0 to infinity e raised to minus st into 1 into dt. Okay, so this is nothing but the Laplace transform of the constant function 1. And what was that value? Just now we had seen in the first example, it was equal to 1 by s. So altogether, I'm just finishing it up over here. Altogether we get L of t is equal to 1 by s into script L of 1, which is equal to 1 by s into 1 by s, which is 1 by s square. So the Laplace transform of the function t is nothing but 1 by s square. Here we are applying the integration by parts method. Okay, now let's see another example to determine the Laplace transform of a exponential function. Third one, L of e raised to say minus 3t. Okay, this will be equal to integral 0 to infinity e raised to minus st into f of t is e raised to minus 3t dt. So this is nothing but 0 to infinity e raised to minus of s plus 3 into dt. Now what will this value be? This is equal to integral e raised to into t, sorry, into t, e raised to minus of s plus 3 into t by s plus 3 minus the limiting value is from 0 to infinity. Again e raised to minus infinity is 0 and e raised to 0 is 1, so just like the first example, this value will become 1 by s plus 3. Okay, so this is always the corresponding value, and this is the case arises, this limiting value should always exist. So that is limit, if we can write this integral as limit b tends to infinity integral 0 to b e raised to minus of s plus 3 into t into dt, right? So both these are same, so this limit should exist, and for this limit to exist, s must always be greater than minus 3, because s plus 3 must be greater than 0, right? That is the only possibility when this limiting value exists. So this is valid for s greater than minus 3, because this integral should exist if s plus 3 is positive. If it is negative, we'll have e raised to some positive value, and e raised to infinity goes to infinity. E raised to minus infinity is 0, but e raised to infinity is some value in infinity itself, so that integral will not exist. So for this whole term to remain negative, the only way is by treating s plus 3 to be greater than 0. S plus 3 must be greater than 0. Okay, so s plus 3 is greater than 0 implies s should be greater than minus 3. So I hope this concept is clear. Okay, now we shall do one more, basic function. So far we have done constant function, then we did a polynomial function, then we did exponential function, and next obviously we'll have to deal with our trigonometric functions. So let us evaluate what is the Laplace transform of the function sine 2t. Okay, so from definition, this is nothing but integral 0 to infinity e raised to minus st into sine 2t into dt. So here again we'll have to use integration by parts. So by integration by parts, this is my first function, and no, this is my first function, this is my second function. So first one is sine 2t into integral of e raised to minus st. What is it? It is again minus e raised to minus st by s, okay, minus of integral of derivative of sine 2t is cos 2t, and the integral of we'll have cos 2t into integral 0 to infinity e raised to minus st dt. So this is nothing but minus e raised to minus st into sine 2t by s varying from 0 to infinity minus what is the integral of e raised to minus st again? There is one more thing, the derivative of cos 2t is nothing but 2 in sine 2t is 2 cos 2t, right? So here it will be minus 2 by s is something which is constant, and e raised to minus st is e raised to minus st. I hope you are getting the integration by part concept clear. Okay, this is the derivative, this is the first function, this is the second function. The first function remains as it is in the first term, and we'll integrate the second function, and in the second term it will be negative. There will be an integration of derivative of the first function. So derivative of sine 2t is nothing but 2 cos 2t, and into integral of the second function. So the integral of second function here is again e raised to minus st by s. So there is another integration, again we have to integrate it. So altogether this is the value that is remaining. Now let us now apply limit in this case. Here again e raised to minus infinity is 0. So again I am repeating, e raised to minus infinity is 0, e raised to infinity goes to infinity. Okay, so for that s must be positive, for that case to be happening. So this Laplace transform will be defined for all values where s is greater than 0. So e raised to minus st, this e raised to minus infinity becomes 0, and the next value for t is 0. So e raised to 0 is 1, but sine 0 is 0. So again this term reduces to 0, right? So this becomes 0, and what else do we have? We have plus 2 by s into integral 0 to infinity e raised to minus st cos 2t dt. Okay, so here again we'll have to apply the same process, that is integration by parts. So L of sine 2t, script L of sine 2t is 2 by s integral 0 to infinity e raised to minus st cos 2t dt. Now we'll have to again proceed by the integration by parts method over here. So here let's do it again. L of so by integration by parts, what do we get? This is 2 by s, the first term, that will be minus of e raised to minus st into cos 2t by s minus, and we'll have 2 by s integral 0 to infinity sine 2t dt. Okay, So e raised to minus infinity is again 0, and here we'll have e raised to 0 is 1 and cos 0 is also 1. So here we'll have a term that is 1 by s, minus of minus 1 by s. So that will be 2 by s, 1 by s minus 2 by s. And what is this? This is actually nothing but L of sine 2t itself, right? Sine 2t. So this is 2 by s square minus 2 into 4, 4 by s square into script L of sine 2t. So from this we'll determine the value of sine 2t, script L of sine 2t. How do we get that? So by taking this to the other side, I'll get 1 plus 4 by s square into script L of sine 2t is equal to 2 by s square, that is s square. So this is equal to, this implies script L of sine 2t will be equal to, this becomes s square plus 4 by s square. So when I take it to the other side, it becomes s square divided by s square plus 4. S square and s square gets cancelled, so it will become 2 by s square plus 4. This is the Laplace transform of the function sine 2t. Okay. So this is the method or the procedure to determine the corresponding Laplace transform of a given function. So we have discussed the Laplace transform of some common functions like constant function and polynomial, exponential, trigonometric. And if you can see that in all the examples, the solution or the answer, the final answer, is in terms of s only. That is what I had just mentioned, that we write it as f of s or capital G of s or capital H of s. So this is how we determine the Laplace transform. So one must be very much familiar with the concept of integration, especially integration by parts. So just go through the problems that we have discussed, and we shall be doing more problems to determine the Laplace transform of well-known functions. So that's it for today's session. Thank you. Stay safe and stay healthy.